All right, welcome to 13.4, part 2. So now we are using our compounded more than once a year equation, which looks like this. The value at time t is the principal, 1 plus the rate over n t, where n is the number of times per year that the interest is compounded. So they invest $600, that's P, in an account that earns 6.25 annual interest compounded semi-annually, twice a year. And here's the interest. Find when the value of the investment reaches $1,700. So equation 1 that we'll graph, simply taking this and I'm plugging in what I know. N is 2 to the 2 times t. All right, the second equation we'll graph is when will the value be 1,700? So we need to see the intersection here, right? So again, I'm always saying, what will our window need to be? So we're starting at $600. Whoops. Okay, and we want it to grow to 1,700. So our x, we're going to say, excuse me, y min, we can say is 0. Y max, why don't we make it $2,000? Then we can see everything going on. Now this money, they're asking it to grow more than double. And that's going to take a while. So if we start at an x min of 0, I would say let's put an x max of 30 years out there. Let's see what we get, right? So I'm going to graph these two equations. All right, 600 raised to the 2x. Boy, I hope I put that equation in right the last time. 1,700. I'm going to graph it. Well, I didn't change my window yet, but let's see what we got. It's thinking. All right, well, this is the window from the last equation, and I do not see the intersection. So let's look at what the window was. Oh, I only had it going to 15 years. Actually, this was the same. That's good. But now I'm going to change this to 30. I'm going to change x max to 30. And I should be able to see my intersection. Yeah, I'm going to see it pretty easily because the graph looks like it's doing this. It's thinking. All right, so we're going to see the intersection. Second, trace, intersect. First curve, second curve, guess. So it's actually 16.9 years. It'll take 16.9 years for the value of that investment to be $1,700. So every problem we've done so far in this section, folks, has the same process. We just use slightly different equations based on whether we're compounding interest once a year or more than once a year. Right, now let's talk about compounding interest continuously. This is almost something we can't get our head around because it's taking the compounding n and making it approach infinity. So when you have an equation like that, someone has developed this equation and it uses that base e from 13.3. So here is our value equation. Let's apply it. We're not sure how they got it, but let's apply it. So if a person invests $5,000, that's our principal, earns this much interest compounded continuously. Find when the value reaches this. So again, two equations. The first equation will be $5,000 e to the RT. So this is a slight, it's a different equation. Right? Then when will this reach $12,000? Right? I'm going back. We're graphing a bunch of equations here, aren't we? So I'm e to the 0.035x in this case. Now again, let's look at 0 on the y needs to grow to 12,000. So why don't we give it a max of 15,000? And then I'm not sure how long it'll take, but look at, we're more than doubling. So let's give it 20 years maybe on our x. So x min will be 0. X max will start with 20 years. Y min will be 0. Y max will be $1,500. I want to update my window. I'll do the 20. I'll have to put 15,000. Let's graph it. Not sure it's going to hit. Well, maybe it does. I don't see it. It's doing this. I don't see an intersection yet. So I need to open that up a little further, don't I? So I'm going to take my X max, and I'm going to make it 30 years. X max, 30 years, so I can see what's going on. So I'll take these lines out of here. Now, it's doing this, and I have an intersection. Second calc, go down to my intersection. First curve, second curve, guess. It says at 25.01 years, which is for all intents and purposes, 25 years, it'll take me 25 years to get a value of $12,000. Not bad, right? Now, these equations up here, folks, you're not going to have to memorize them, but you will have to know when to use them. So here's another example. Now, this is the right answer. Let's make sure we can get it. So our compounding continuously is the value at time t. I always call it PERT, P to the ERT. So the value at time t, here's our principal, 1550, e to the 0.04t. They're saying, when will it reach $2,000? Well, it's not growing that much, but I'm going to say, I'm going to take it up like along the y. I want to be able to see the intersection, so I have to include these values. So I'm going to say my y min is 0, my y max is 2200, and it doesn't have to grow that much. So I'm going to do an x min of 0 and an x max of 10 years. All right, so we're graphing another set of equations. 1550 e 0.04t or x, 2000. I'm going to change my window. 0 to 10 on the x, 0 to 2200 on the y. Let's see what our graph looks like. I'm going to see it. Just doing something like this. So I can find that intersection. Second calc, intersect. First graph, second graph, guess. At 6.4 years, oh my gosh, that's what they had. The value of that investment will be $2,000. All right, so, so we've talked about compounding once a year, annually, compounding more than once a year, semi-annually, quarterly, etc., and compounding continuously, right? Now, what if you get in a situation where you have to compare different investments? How do you know which one's best? You know, if one of them is calculated annually or compounded annually versus another one that's compounded maybe, you know, quarterly, how do you make it so you can compare them easily? So they have this effective, that means what am I actually getting annually? Effective annual interest rate.